According to legend, Galileo once dropped 2 balls weighing different amounts from the top of the Leaning Tower of Pisa in order to test whether heavier objects fall faster. Whether this experiment actually happened or not, it reveals something essential about the scientific method. Galileo could control everything that determines the speed of a ball to cleanly test his hypothesis. But here's what makes this story perfect for empirical economics. Even if Galileo had the perfect answer to how fast a ball falls from the Leaning Tower of Pisa, scientists of his day still might wonder how fast a ball falls on a different celestial body like the moon or Mars. This example of falling balls leads to a greater question that relates to empirical economics and indeed to science more generally. And that's a question of internal versus external validity. Galileo's experiment had perfect internal validity. He controlled everything about the ball's speed, including weather conditions, how high the ball was above the ground, and where it was in the tower. The only variation that remained was deliberate variation that defined the treatment of the ball, whether the ball was heavy or light. In economics terms, this was a perfectly controlled experiment. Everything about the treatment and control groups was identical except for the treatment. And this is why he could do his experiment with just 2 balls instead of 10 in each group. But the main problem is that his result only applied to the Leaning Tower of Pisa, or, depending on how you think about it, anywhere on the Earth, but not anywhere else in the universe. External validity asks, would this result hold in other contexts? For Galileo, the other contexts would be areas of Earth outside of Pisa or areas of the universe outside of Earth. These types of questions also are common in economics, where we might run an experiment on a job training program in the United States, and we might wonder if the results generalize to a different country or a different part of the United States. This is the problem of generalizability. Clean identification provides internal validity, but what we need is external validity. We need to know how it applies elsewhere. About 100 years after Galileo, Sir Isaac Newton answered this question, but he didn't do it with more experiments, he did it with theory. He proposed that falling objects obeyed a deeper fundamental law, which we now know as Newton's law of universal gravitation. This theory-based approach that Newton took is exactly what economists call structural modeling. Newton proposed that observable behavior reflects stable underlying parameters. These parameters don't change across contexts, and even though surface results may vary, the mechanisms stay constant across contexts. Newton was estimating the economic equivalent of preferences and technology, the deep parameters that generate behavior everywhere. Newton's approach is particularly elegant because it explains not only behavior at the Tower of Pisa, but anywhere in the universe. If you want to know how much you would weigh on Mars or the moon, Newton's law can provide that answer. All you need to know is your weight on Earth and the mass and radius of the new planet. It took almost 400 years for Galileo's original experiment to be validated outside of Earth. In 1971, astronaut David Scott dropped a hammer and a feather on the moon and observed that they fell at exactly the same speed. But the irony is that astronauts couldn't have even gotten to the moon to run that experiment if they didn't have Newton's law of universal gravitation in the first place, as well as other physics discoveries that followed it. In modern economics, we face the exact same opportunity. We have less structural approaches that are akin to Galileo's experiment, where we can get excellent internal validity through randomization, but that can only tell us about that particular context in which the experiment was run. Then we also have more structural approaches like Newton's, where we can estimate deep parameters like preferences or production technology, and we can use these approaches to tell us how people would behave with policies that have never been actually implemented before. Just as Newton could predict your weight on Mars, more structural models can predict, for example, how a cash transfer program in India would generalize to Kenya. You might be wondering how this is possible. The answer is that it relies on mechanisms, and it also relies on a model to extrapolate beyond the current context. Because economics is much more complicated than physics, some economists might say that all extrapolation is useless, and hence no economics results are actually externally valid. But in truth, the best empirical work combines both internal and external validity, or less structural and more structural methods to arrive at externally valid laws. And to get there, we can follow a similar process as Galileo and Newton. We can start, like Galileo, by using experimental methods to isolate clean identification in a particular context. Then we can think like Newton by building theories about why the experimental results were the way they were in the original context. Finally, we can be like the moon mission and test these models in new contexts to see if the mechanisms hold up. And finally, if the theory doesn't hold up, we can be like Einstein, who discovered shortcomings in Newton's fundamental law of gravitation and generalized it to form his law of relativity, or his theory of relativity. Again, this isn't structural versus reduced form, it's optimizing trade-offs along a spectrum. External validity is not about running experiments everywhere. It's about understanding the forces well enough to be able to predict what's going to happen in new contexts.